In this talk, I will describe how to accelerate Bayesian inference for computationally expensive models. This approach utilizes a multi-fidelity hierarchy of models within a SMC algorithm called Sequential Tempered Markov Chain Monte Carlo to efficiently sample the Bayesian posterior distribution. First, I will present an overview of Bayesian inference in Markov Chain Monte Carlo, known as MCMC. Then I will describe a sequential Monte Carlo algorithm called Sequential Tempered MCMC, which can be used for solving Bayesian inference problems. Then I will describe a multi-fidelity approach to accelerating sequential tempered Markov Chain Monte Carlo. Finally, I will present 3 example problems for system identification within gene regulatory networks. Then I will conclude. Within Bayesian inference, we use probability distributions to represent our uncertainty due to insufficient information about a system. As data become available, however, we're able to update this distribution to reflect this new understanding. And then when we want to make predictions, we need to propagate this uncertainty to the quantities of interest that we're interested in. Bayesian methods are critical for many types of systems, particularly those where there is a lot of uncertainty, so we need to really quantify it rigorously. Methods like Markov Chain Monte Carlo are used to solve these Bayesian inference problems. However, it's very computationally expensive because they often require tens of thousands to millions of model evaluations to get a representation of the uncertainty in the system. So for computationally expensive models, this is prohibitive. One approach to try to rectify some of these challenges is to use a multi-fidelity hierarchy. Often, computational models exist in varying levels of fidelities or accuracy, so it may be possible to use lower accuracy models to speed up the MCMC process. The question that we need to answer is, how do we know when to use each of the models in the multi-fidelity hierarchy? The Bayesian inference problem begins with a prior distribution over our model parameters theta. In this diagram, we show the prior on the left, which represents the model parameters, conditioned on a specific choice of model M. As data becomes available, these observations are used to update this prior distribution through Bayes' theorem, which describes the posterior probability, the probability of theta given the data in the model, is equal to the probability of the data given theta in the model, which is called the likelihood, times the prior, the probability of theta given the model, divided by normalization factor, the probability of data given the model. Often we cannot work with these distributions directly because they are analytically intractable. However, we can use Markov Chain Monte Carlo to draw samples from the posterior distribution, where you have a Markov chain that explores the posterior and has the posterior distribution as its stationary distribution. These samples can then be used for posterior estimation. So if we are interested in a quantity of interest G, we can calculate the expected value of G from the sample population. However, because there is correlation from the Markov chain, the error on this estimate is not simply just the same error as if they had been independent samples. Finally, we might not just be interested in estimating the model parameters theta or expectations of quantities of interest. We might be interested in comparing different potential model classes that could describe a system. In this case, we need to calculate the model evidence for a given model M. In fact, this is just the normalization constant, the probability of data given the model, which becomes the likelihood within this model's comparison problem. As we will see later, it's important to understand how well we've solved the Bayesian inference problem using sampling, and also how much information we have learned through Bayesian inference. To evaluate the performance of our sample of populations that we've found through a process like Markov Chain Monte Carlo, one important indication that it's a good population of samples is how well it can perform posterior estimation. So if we're interested in estimating a quantity of interest G as an expectation over the posterior, how well do samples from the sampler estimate that quantity of interest? To do this, we can use a property known as effective sample size. The effective sample size of a sample population is the equivalent number of independent samples that will provide an equal quality estimate as our correlated or weighted sample of population that we got from our sampler. Having a high effective sample size means that there'll be low variance in our quantity of interest estimate, Conversely, if there's a low effective sample size, this is reflective that the sample population has a lot of degeneracy or really high correlation, therefore does not represent the posterior well for doing expectations. It is also important to measure how much information we've learned due to inference, or really in between any changes in probability distributions, whether it's from prior to posterior or some other sets of distributions that we're interested in measuring changes in. To do this, we have to define our yardstick for measuring information. In this case, we call this the state of belief R of theta, or the view of expectation. We can then measure the change in belief from Q to P in the view of R. This means that if P is closer to R than Q is, in this information theoric measure, which is like a distance, then the value will be positive. If Q is closer to R than P is, then this quantity will be negative. So we can really get a notion of whether this change of belief from Q to P increases or decreases our information in our view of expectation. If one of the distributions is the view of expectation, then it does just simplify to a KL divergence. So if we want to calculate the information gained to inference, it's just a KL divergence between the prior and the posterior. Now that I've described the general setup of Bayesian inference problems, I'll describe methods for solving them based upon Markov Chain Monte Carlo and Sequential Monte Carlo, specifically the Sequential Tempered MCMC algorithm. Sequential Tempered Markov Chain Monte Carlo is a type of sequential Monte Carlo method, and that means that it uses a population of parallel chains to gradually explore the space and converge the posterior distribution. By having this population of parallel chains, not only can it use high-performance computing resources, but these chains can adapt and learn from each other to speed up the way in which they converge the posterior distribution. ST-MCMC evolves the parallel chains through a series of intermediate distributions gradually from the prior to the posterior. By breaking this problem up into a series of intermediate steps, it is much more tractable. ST-MCMC is really robust and can solve a number of challenging parameter estimation problems and sample posterior distributions that are multimodal because of these parallel chains. Also, because of its robustness, is able to solve model selection because it can estimate the model evidence effectively. ST-MCMC combines three basic steps. First is annealing, which introduces a series of intermediate distributions as we break the problem up from moving from the prior to the posterior. Secondly is MCMC, which is how the population parallel chains explores each of the intermediate distributions. And finally is importance resampling, which is how we transform from one intermediate distribution to the next distribution. ST-MCMC is a form of sequential Monte Carlo, and there's a number of other algorithms that fit within this class. In the annealing step of ST-MCMC, we first define a set of intermediate distributions. These intermediate distributions are going to reflect different amounts of contribution of the data. This is controlled by a parameter beta, which is an exponent of the likelihood. So beta 0 corresponds to the prior, and beta equals 1 corresponds to the posterior. By tuning this beta parameter, we can define how much influence the data has at any given level of ST-MCMC. We then want at every level to choose an appropriate beta so that we can break this problem up into a series of gradual transitions from the prior to the posterior. It is much easier to transform a sample population through these intermediate levels than directly try to jump from the prior to the posterior. This is particularly true for things like multimodal distributions. We can also think about defining these intermediate distributions not just by annealing, but then later on, we'll see that we can do this using the multifidelity hierarchy. The key step in ST-MCMC is determining the intermediate distributions. We do this by determining a delta beta that defines how we move from one annealing level to the next. We don't want annealing levels to be too close together, but if they're too far apart, the sample population at one level is really not sufficient for the sample population to the next level, and so they can't really be reconciled when transforming from one level to the next. This transformation is done through importance resampling using weights. These weights are determined by the likelihood of the power delta beta. So if delta beta is very small, close to 0, then the weights are all approximately equal. If delta beta is very large, there'll be large variations in these weights, which causes degeneracy in the sample population, which means that only a few samples have all the weight. The quality of the sampling population can be calculated from these weights through the effective sample size. So when choosing delta beta, we want to do it in a way that preserves a sufficient number of effective samples. This can be captured by the coefficient of variation of the weights. When this coefficient variation is close to 1, that corresponds to an effective sample size of about 1/2. So we want to tune this beta so that we get close to that target. In the next step of ST-MCMC, we need to take this weighted sample population and transform it to a set of unweighted samples that we can then use to start Markov chains. This is done by importance resampling. We use the weights and resample the samples according to these weights using multinomial resampling. This rebalances the population and discards unlikely samples and replicates more likely ones. In the last step of a level of ST-MCMC, we take the population of samples found through importance resampling and use each of them to start a Markov chain that explores the intermediate distribution using MCMC. This is important because the annealing and importance resampling steps decrease the effective sample size of the population. Lots of samples are going to be repeated because they had a high probability of being selected in the multinomial resampling, so now we need to refresh those samples by exploring the intermediate distribution and decorrelating them using MCMC. Any type of MCMC can be used within this step, but typically the proposal distribution is adapted using the information from the previous levels. ST-MCMC can be used to estimate the model evidence for doing Bayesian model selection. This requires estimating the likelihood of the data given the model, where the model evidence is a normalization factor of the posterior distribution. This quantity is an expectation of the likelihood over the prior, and therefore we can use prior samples through Monte Carlo sampling to estimate it. However, typically if the posterior and the prior are far apart, this is going to be a very unreliable estimate. So with ST-MCMC, we can break this up using the intermediate levels and do a Monte Carlo estimate for each of these individual steps. Therefore, we can decompose the model evidence into a product of these CIs, which are these different coefficients that need to be estimated at each level. Estimating them requires taking the expectation of the new contribution of the likelihood with respect to the prior defined by the previous annealing level. This can be done really easily using the sample population already found through the ST-MCMC algorithm. We can now take this all further by integrating a multi-fidelity hierarchy into ST-MCMC. In this case, not only are we going to anneal to define the different levels, but we're going to change the model fidelity. Intuitively, for low annealing levels where you don't have much contribution for the data, a lower fidelity model should probably be sufficient. However, as you increase the annealing factor, you need to increase the model fidelity as you get to the full posterior. This approach has been taken in several other methods, such as the method of Latz et al. Multi-level sequential square Monte Carlo. In this framework, the intermediate level is defined by a choice of the model fidelity M subscript L and the annealing level beta L. And there are really two types of transitions that can occur. The first is tempering, where the annealing factor is adjusted, and the second is bridging, where there's a change in the model fidelity. For this, we assume that there's a model fidelity hierarchy, meaning that a model of higher fidelity is always going to be better than a model of lower fidelity. Given a change in the annealing factor and model fidelity, we then need to transform the sample population from the current intermediate distribution to the next one, just as before, through importance resampling. The weights here are defined as the ratio of the likelihood of the next model fidelity to the annealing factor beta L plus 1 to the current likelihood using the current model and current annealing factor. Taking this approach, we can now define the general multi-fidelity ST-MCMC algorithm. We start by defining a multi-fidelity hierarchy in which there's a hierarchy of models, and we know as we increase some component of the model, they get better and better. We also have to define the corresponding likelihood. Ultimately, we're trying to get to the kth model, which corresponds to the full fidelity model that we use to define the ultimate posterior of interest. We now proceed through ST-MCMC as normal until we get to the next choice of choosing the intermediate distribution. For this, we have to choose the annealing factor and the appropriate model fidelity for the next level based upon the previous level sample population. We do this through some sort of predefined metric, and then define the intermediate distribution accordingly. Given this choice of the next intermediate distribution, we then need to reweight the sample population using the importance weight so that we can resample the population to get to the next level. This transformed set of samples can then be used to seed the next MCMC steps, and ST-MCMC continues through all the intermediate levels until ultimately the sample population is sufficient for capturing the posterior according to the full fidelity model. So the key question within this algorithm is determining the appropriate annealing factor and model fidelity to use at any given level of ST-MCMC. So we'll discuss two approaches. One is the multi-level sequential square Monte Carlo approach, which we call the ESS bridging, and the other is the information theoretic bridging approach that we discuss and develop in this work. So the ESS bridging was developed previously in Latz et al. Basically first begins with trying a bridging step where you keep the annealing factor the same for the next level, but you increase the model fidelity. Given this proposal, you then compute the population weights and determine how you would need to reweight your current sample population to map it to the intermediate level with the next higher model fidelity level. If the effective sample size for this population is still high, then you don't need to bridge and your current model is still doing a good enough job. And so you can temper instead of bridging. Otherwise, if it was too low, it's important to bridge if it degenerates more. So with an information theoretic bridging, instead of relying on the effective sample size as our metric, we are using a notion of information. So first, you propose a tempering step, and then you determine whether this change in the distribution increases or decreases the amount of information that you gain about the ultimate posterior. In this view of information can actually be negative. And so if information is negative in this transition, then you're now losing information about the posterior, but if it's positive, you're gaining information in the posterior. So you want to change the model fidelity if you're starting to lose information from this transition. So discussing these a little bit deeper, the ESS bridging technique is great because it only requires evaluations at the next level and the current level of the hierarchy. So that can make it really appropriate for very expensive models. However, you're not really tracking the full objective of trying to estimate the ultimate posterior. The information theoretic bridging, however, is trying to track this ultimate objective of estimating the posterior, but as a consequence, it needs some posterior samples of the full model to estimate the information. So even though it's reducing significantly the number of full model evaluations needed, it still requires some full model evaluations throughout the algorithm. So for an extremely expensive model, this may not be appropriate, but we find in our experiments that it works fairly well and does better than the ESS bridging in terms of computational cost. After bridging, the annealing factor can also then be tuned to an ESS target. So instead of just changing the model fidelity when you're bridging, you may also want to change the annealing factor as well. This could be because that jump in level is reducing the effective sample size too much, so you want to back off lowering the annealing factor to regenerate some samples, and so you're not over-biasing your results. Or maybe the levels are still close enough to where you can make a little bit of an annealing step for speeding up the computation. So we can see some of these trajectories in one of our experiments where we look at these three different results. So we see that the ESS bridging and the IT bridging are only taking these horizontal vertical lines, but this tuned trajectory can effectively choose both the annealing factor and the model fidelities. Now we can dive into the information theoretic criteria that we use for evaluating whether our annealing step loses or gains information about the ultimate posterior that we're trying to sample. So we need to measure the information gain or loss from the current level of annealing to the next level of annealing conditioned on using the same model fidelity in the view of the posterior. However, we just need to estimate the sign of this information measure because we don't need to know what the actual amount of information is, just whether information is gained or lost, which is either because it's positive or negative. To do this, we express this as an expectation with respect to the full posterior distribution with the full fidelity model. We obviously don't have samples from the full posterior to estimate this integral, so instead we have to use importance sampling to estimate it using samples from the current level of the ST-MCMC algorithm. Once we have samples from this population, we can estimate the different quantities of interest within the integral. We note that when you do this transformation, you lose the absolute magnitude of this integral because there's a ratio of model evidences that needs to be factored out, so we only know it up to constant proportionality. However, because we're only interested in the sign, since the model evidences are always positive, that doesn't affect the sign of the information. So then we can construct our information criteria where we have to compute 3 different expectations. Computing these expectations does require a set of full model evaluations at the samples from the current level, but not nearly as many full model evaluations as if we had used the full model for the MCMC steps. We can now apply multi-fidelity ST-MCMC to a series of example problems for inferring parameters of stochastic reaction networks in biological systems. This is joint work with Hui Vo and Brian Munsky at Colorado State University. Modeling gene regulatory networks in cells takes the form of a stochastic reaction network. This is often modeled using the chemical master equation, which is a continuous time discrete state space Markov process, in which the probability of a cell being in a given state is evolved according to this linear dynamical system, parameterized by a matrix A that describes the probability that within a unit of time, the cell will transition from one state to another. We observe the number of counts of different chemical species within a cell, called the copy number, at different points in time. The states are, as I said, the probability that the cell has a certain number of each of these species, and the parameters of this model correspond to the propensity of certain reactions. So there's certain reactions of different molecules coming together and forming new molecules that have different rates of occurring. Theoretically, this matrix has an infinite dimensional space as the number of molecules is not bounded. However, for both practical and computational reasons, a finite state projection algorithm is used to limit the maximum number of any of the given chemical species, with an absorbing state when the maximum number is exceeded. So for our surrogate models, for our multi-fidelity hierarchy, we use different numbers of maximum molecules within the finite state projection algorithm. So you can see this in the graphic here, where for the full trajectory in blue, we approximate it using a series of smaller FSP projected CMEs in which we limit the maximum number from 40 to 60 to 100, and you can see how you can increasingly recreate the full chemical master equation solution. For early levels of ST-MCMC, we don't really need the full complexity of the CME, and we can use these smaller surrogates for computational efficiency. By limiting the size of the state space, you significantly reduce the size of the matrix A, which makes it significantly computationally faster. For our first example, we look at the Repressilator gene regulatory network, which is a negative feedback circuit for 3 different chemical species. Each of these chemical species is either created or destroyed according to different propensities, which are defined with certain model parameters A, gamma, and K. We are trying to identify these model parameters using Bayesian inference with synthetic data. We can see that all the different methods between the full fidelity, the ESS bridge, the IT bridge, and the tuned IT bridge recover the same posterior distributions, meaning that the ST-MCMC algorithm with the multi-fidelity models is as good as the full fidelity solution. We find that multi-fidelity ST-MCMC is able to provide significant speedups over the full fidelity ST-MCMC method. At the initial annealing levels, the ESS bridge method is fastest because it doesn't require full fidelity model simulations to guide the sampling. However, as the algorithm progresses, the better choice of intermediate levels by the information theoretic criteria allow it to be computationally more efficient overall. From this plot, we can see that when the annealing factor is below approximately 1/10, the lowest fidelity simulation is sufficient for guiding sampling. It is not until we get close to the posterior that the model fidelity needs to be increased. We can see that the information theoretic bridging chooses to bridge after the ESS method because they assess that the lower fidelity model is still useful when trying to fit the full posterior. Finally, we can see that both the ESS bridge and the IT-tuned bridging methods actually are able to reach their final level without needing to get to the full fidelity posterior. This means that the sample population made with the lower fidelity model is actually sufficient for important sampling the highest model fidelity. So the highest model fidelity actually never needs to be used within MCMC. Finally, on the left, we can see trajectories that are taken through parameter space as the annealing factor increases for different model parameters. We see that for almost all the parameters, all four methods take very similar trajectories to the space. The only different parameter is gamma 1, in which the information theoretic methods choose to bridge later, and so they have more bias being introduced in their parameter estimate. However, the information theoretic criteria judges that this amount of bias is acceptable, and we see indeed is able to correct for it very quickly once it chooses to bridge levels. In the second example, we try to use Bayesian model selection to compare different models for compartmental gene expression. Within these models, either a 2, 3, or 4 gene state model is used to model the transcription, transportation, and degradation of nuclear mRNA into the cytoplasm. We generate synthetic data from this system and try to use multifidelity ST-MCMC to identify the different likelihoods of the different models. We choose the tuned IT bridging technique because it is more robust than the other methods, which is important for performing the thermodynamic integration that is necessary for computing the model evidence. With this method, we observe speedups of 1.6, 3.8, and 3.2 times for the 2, 3, and 4 gene models respectively. The slower speedup for the 2 gene model is because that model is fairly computationally efficient to begin with. We see that the model evidence estimates found with the tuned IT bridge ST-MCMC method compare favorably with the full fidelity estimates that we get using normal ST-MCMC. In fact, the tuned IT bridging methods have a lower error because they take more intermediate distributions as they travel from the prior to the posterior, and therefore the thermodynamic integration can be more accurate. In our final example, we are trying to infer the values of parameters in an inflammation response model of the gene IL-1 beta. This has 3 gene states and RNA. There are 11 parameters, and we have real data from a series of time points shown on the right. We can see that when we fit this model using ST-MCMC with the different multifidelity methods in the full model as well, we are able to recreate the data fairly accurately, and all the different fits are on top of each other, indicating that they converge to the same posterior distribution. When we see the posterior distributions identified through the 3 multifidelity methods and the full fidelity ST-MCMC, we see good agreement between these distributions. In this example, we see speedups between 1.7 and 2.2 times. This is a decrease in computational cost, although because the full fidelity model has a state space size that isn't too large, an order of magnitude smaller than example 1, we do not see as large speedups. We can investigate the relative performance of the different multifidelity ST-MCMC methods. We see that initially the ESS bridging technique is computationally faster because it chooses to wait longer in the annealing process before choosing a higher fidelity model. In contrast, the information theoretic bridging techniques bridge earlier. However, they spend more time at these intermediate annealing levels compared to the ESS-based bridging technique, which almost instantly transitioned to the highest fidelity model after leaving the lowest fidelity model. Therefore, overall, the information theoretic bridging techniques are slightly computationally more efficient. We also see that the tuned information theoretic bridging technique actually has to often backtrack, meaning that when it changes model fidelity, it has to decrease the annealing coefficient to compensate for the decrease in effective sample size caused by changing the model fidelity. This indicates that the intermediate distributions defined by the different levels of the multifidelity hierarchy are actually relatively far apart. We can also look at trajectories through the parameter space as a function of the annealing factor. We see that there are significant variations between the different trajectories taken by the ESS bridging technique and the information theoretic bridging techniques. We see that the different parameters, for example R1, B10, and K12, show significant deviations for the ESS bridging estimate. This could be because the ESS bridging is judging whether the bridge based only upon the next level and not the final posterior, and so therefore it has kind of a myopic approach to bridging. Therefore, even if two adjacent distributions are close together, they might not actually be informative when trying to reach the ultimate high-fidelity posterior. Therefore, we see bias accumulating, although it is finally corrected once it switches to full fidelity model. In this talk, I've described multi-fidelity sequential tempered Markov Chain Monte Carlo, which is a way of integrating a multi-fidelity hierarchy into a sequential Monte Carlo algorithm for solving Bayesian inference problems and Bayesian model selection problems. This model fidelity hierarchy is used to accelerate sampling by using a lower fidelity but also lower cost model at the initial stages of the sequential tempered Markov Chain Monte Carlo algorithm, where the algorithm is trying to converge to the posterior distribution. Once sampling the posterior, the higher fidelity models can be used. We introduced a novel information theoretic measure for determining the appropriate model fidelity to use at each level in the sequential tempered Markov Chain Monte Carlo algorithm. This augments the existing effective sample size-based methods for choosing the model fidelity to be used at any given level. This information theoretic measure provides a principled way for choosing the model fidelity based upon whether the current model fidelity still provides information about the ultimate posterior. We illustrated this approach on 3 example biological problems for inferring parameters and doing model selection within stochastic reaction networks of genetic circuits within a cell. We find that the multi-fidelity methods provide equivalent results to the full fidelity method, but at much less computational cost. Thank you very much for listening to this talk. I'd like to thank ST-MCMC for hosting this online conference. If you have any questions, please feel free to reach out or refer to our paper that is coming out in the International Journal of Uncertainty Quantification.